Welcome to the Deep Dive, where we take a stack of sources, dig in, and pull out the most important insights for you. Think of it as your shortcut to getting genuinely well-informed. Today, we are plunging into the incredible world of stellar modeling. Imagine trying to understand what's happening inside a massive, burning ball of gas, billions of miles away. How do scientists figure out its structure, how it evolves over eons, when we can't possibly see inside?
That's precisely the challenge. And this deep dive is based on excerpts discussing how scientists build these sophisticated numerical models of stars and their evolution. And critically, how a flood of new data, particularly from the European Space Agency's Gaia mission, is fundamentally changing how we do that.
Right. So our goal for you today is to walk through the fundamental process of building these stellar models, explore the key physical challenges involved, and see how these vast new observational data sets, especially the torrent from Gaia, are really pushing the boundaries and forcing scientists to refine their theoretical models at an unprecedented pace.
And it's important to remember why this matters. Understanding stars is absolutely fundamental to understanding the universe itself, how elements are created, how galaxies form and evolve, even the environments where planets are born. And since a star's interior is completely inaccessible, modeling combined with increasingly precise observations is really the only way we can hope to unlock their secrets.
Okay, let's unpack this then. When we talk about a stellar model, what exactly are we building? What does that mean?
Well, at its core, a stellar model is a sophisticated numerical code, a computer program, basically. The groundwork for these codes was laid decades ago, actually. Pioneering work in the late 1950s by people like Schwarzschild and Henney. These codes use fundamental physics to calculate the star's internal structure, things like temperature, density, pressure, at every point from the center right out to the surface. And then they predict how that structure and the star as a whole will change over millions or billions of years.
And what drives that change? What's making the star evolve?
The essential engine of stellar evolution is the slow but relentless change in the star's chemical composition. This change is caused by nuclear reactions, mainly fusion, happening deep inside the core. As lighter elements like hydrogen are fused into heavier ones like helium, and then later, say, helium into carbon and oxygen, the physics of the star's interior shifts dramatically. That forces the star to adjust its structure and how much energy it puts out.
Okay, so these models must be built on fundamental physical laws. What kind of equations are they actually solving?
Yeah, they solve a set of coupled differential equations based on really core physical principles. Conservation of mass, the total mass stays the same even if it moves around inside. Conservation of energy generated in the core has to make its way out eventually. Hydrostatic equilibrium, that's the balance, right? The inward pull of gravity is balanced by the outward push of pressure at every single layer inside the star. And the equations describing how energy gets transported from the hot interior to the cooler surface, that can be through radiation, convection, or sometimes conduction.
And these are all linked together.
Exactly, they're coupled. You have to solve them together. And they need specific boundary conditions, what things are like right at the star center, and what they're like at its outer surface.
Wow, that sounds like it requires pulling in physics from all over the place.
It absolutely does. To build these models, you need inputs from many different branches of physics. You need nuclear and particle physics for reaction rates, and also for how opaque the stellar material is, that's opacity, basically how easily radiation travels through it. You need atomic and molecular physics, thermodynamics, hydrodynamics to understand how the gas moves, and radiative transfer, which describes how light and radiation move through the star's layers. It's a huge synthesis.
And I think you mentioned earlier, or the source material did, that one area, convection, is particularly difficult, that hydrodynamic part.
It is, yeah. It's a major challenge in stellar modeling. Convection, where hot plasma physically rises and cooler plasma sinks down, it's incredibly complex to simulate accurately in 3D. So the source mentions that stellar evolution codes often use simplified or phenomenological descriptions for convection. Things like the mixing length theory or overshooting. These are sort of approximated ways to figure out when convection happens and how much heat gets transported by this bulk motion.
But getting those approximations right is key.
Oh, absolutely crucial for predicting the structure and evolution accurately. But it's tricky because we can't actually see the convection happening deep inside the star.
Okay, so you build this really complex theoretical model based on all this physics. But like you said, you can't see the core. How do you know if the model's predictions about what's happening inside are, well, correct?
This is exactly where observations become indispensable. We can't peer directly into the deep interior, no, but the consequences of what's happening inside are observable, either at the star's surface or through its overall
Like
properties.
what kind of things?
Things like its total luminosity, its intrinsic brightness, its surface temperature, its physical size or radius, its mass, the chemical elements we can see on its surface through spectroscopy, and even tiny vibrations or oscillations within the star.
That's astroseismology, right?
Exactly, astroseismology. All these things provide vital clues, so better observations give us stronger constraints that the models absolutely have to match.
What specific kinds of observational data are most useful then for testing these stellar models?
Scientists use a whole range of data types. Bolometric luminosities are really key. That's the total energy output across all wavelengths. You get this by combining the star's apparent brightness, how bright it looks to us, its distance, which is crucial, and corrections for how its light is distributed across the spectrum. Those are the bolometric corrections.
Okay, what else?
Surface chemical composition. That's determined through spectroscopy, splitting the star's light into a rainbow to see the specific fingerprints of different elements absorbing or emitting light. Mass is best measured, most accurately anyway, for stars in binary systems where we can actually watch their orbits.
And then things like temperature and size.
Yep, the star's effective temperature, TEF, its physical radius, and increasingly important, as we mentioned, the frequencies of those internal oscillations measured by astroseismology.
Now, before this recent flood of data, was there a particular mission in the past that really moved the needle on testing models?
Yes, definitely. The Hipparcos mission, its main results came out in 1997, and it really represented a significant leap forward. It provided much, much better distances for about 120,000 stars, mostly relatively nearby ones, within about 100 parsecs or so.
And getting those more accurate distances, what did that let astronomers do?
Well, it enabled them to calculate much more accurate luminosities for a really large sample of stars. Stars across different populations, different evolutionary stages, stars in different parts of our galaxy, in clusters, different types of variable stars, even faint white dwarfs. It also helped characterize binary star systems much better and provided really comprehensive data on their brightness and variability over time.
So it sounds like a big success for constraining the models.
Absolutely. Huge success. But interestingly, while Hipparcos was great, the increased precision of its data also started to reveal problems. It highlighted shortcomings in the existing stellar models.
How so?
Because the distances were suddenly so much more accurate, the uncertainties in other stellar parameters became much more obvious.
Like temperature or composition.
Exactly. Things like effective temperature, surface composition, surface gravity, mass, radius. The errors in those became more glaring because the distance error was so much smaller. The models weren't always matching the precise Hipparcos data as well as people might have expected.
Right, so by nailing down one crucial variable, distance, it basically exposed how much uncertainty there still was in our understanding of the other pieces of the puzzle.
Precisely. And there was another limitation, too. Its distance horizon, that 100 parsecs or so, meant it mostly observed nearby stars. That limited its view of rarer but really crucial stages of stellar evolution, stages that might happen quickly or just aren't very common nearby.
And this is where Gaia comes in, right? The European Space Agency's mission.
Yeah.
How was it designed to sort of overcome those Hipparcos limitations?
Yeah, Gaia. The source highlights that Gaia was designed specifically to push way past those boundaries. Its goal wasn't just to measure positions and motions via astrometry, although it's doing that for nearly 2 billion stars, which is incredible in itself. But crucially, it was designed to simultaneously establish their detailed nature.
What does detailed nature simultaneously mean, practically speaking?
It means that in one single mission, Gaia is collecting multiple types of data for pretty much every star it sees. It gets highly precise astrometry position, distance via parallax, and how it moves across the sky. That's proper motion. It gets photometry in multiple color bands, telling us about the star's brightness and temperature. And for the brighter stars, it gets spectroscopy, revealing their composition and radial velocity, how fast they're moving towards or away from us.
So it's getting this whole suite of data all at once.
Yes. By collecting all this data together, it provides a much more complete picture of each star right from the get-go.
And the sheer quantity of data is just staggering. What are the sort of headline numbers from Data Release 3, for example?
Oh, it's immense. Even based on just the first 34 months of observation, DR3 is huge. It includes astrometry and photometry in the main G-band for 1.8 billion sources. Think about that. 1.8 billion. It provides a full 5-parameter solution, position, parallax, proper motion for 585 million stars. We get mean photometry in the other color bands for 1.5 billion objects. There's data allowing spectral types to be determined for 217 million stars, radial velocities for 33 million, variability classifications for 10 million, and even rotational velocities for about 3.5 million stars. It's just an unprecedented census of our galaxy.
So how does this massive data set specifically help scientists studying stellar evolution? What's the connection?
It makes an enormous contribution because it provides this detailed information across a vast range of stellar populations,
Hmm.
and importantly, across a wide variety of evolutionary phases, including those rarer ones that were so hard to catch before. By characterizing millions of variable stars, for instance, Gaia provides critical data points that are directly linked to different evolutionary stages.
Variable stars. What kinds are particularly important here that Gaia is helping with?
Well, the source mentions Gaia has characterized something like 140,000 aurora Lyrae stars, and it gives details like their pulsation periods, their brightness amplitudes, even estimates of their metal abundance based just on the photometry. It's done this for 9,000 Cepheids, too, another key type of pulsating variable again, with photometric metal abundances.
Those are the standard candles, right? Important for distances.
They are, yes, but their pulsation properties also tell us a lot about their internal structure and evolution. Gaia also covers long-period variables, shorter-period pulsators like Delta Scuti and SX Phoenicia stars. And significantly, it's characterized 150,000 Biguae Draconis stars. These show brightness variations because of star spots and rotation. That gives us crucial data on stellar rotation rates and indirectly helps constrain stellar ages, especially for lower mass stars where age dating is really hard.
Why is characterizing variable stars so important?
It's vital because their pulsations or variations are often directly tied to their internal structure or recent evolutionary events. What's happening inside causes the variation we see outside. Gaia's huge sample size lets us study these phases, these specific moments in a star's life, in just exquisite detail across the whole galaxy.
Okay, so Gaia is clearly revolutionary. But the source also stresses it's not working in isolation, right? It's part of a larger ecosystem of data collection.
That's exactly right. While Gaia is providing this incredible bedrock of astrometry and photometry for billions of stars, many other complementary projects, both current and future, are contributing vast amounts of data that are absolutely essential for testing and improving these stellar models.
Can you tell us about some of those other crucial projects? What else is feeding into this?
Sure, there are space missions focused specifically on high-cadence photometry. That means they measure stellar brightness very, very frequently, like multiple times an hour or even faster. Missions like Kepler, its follow-up K2, the current TESS mission, and looking ahead, the future Plato mission. These provide the kind of detailed light curves, the brightness measurements over time needed for astroseismology.
Right, astroseismology, again, listening to the star's vibrations. What kind of data does that provide that maybe Gaia doesn't do as well?
Astroseismology gives us incredibly accurate information about a star's internal structure. Its density profile, how density changes from the core outwards, even its rotation profile deep inside. For stars similar to our Sun, missions like Plato are aiming to provide radii and masses accurate to about 2% and ages to around 10%. That's phenomenal precision.
Wow.
And critically, astroseismology can also provide distances that are independent of the geometric parallax method that Gaia uses.
So it's a different way to measure distance.
Yes, and that's invaluable, both for cross-checking Gaia's distances, making sure they're accurate, and for providing distances for stars where maybe Gaia's parallax is less precise for some reason. It really strengthens the overall foundation for our models.
What about other big surveys? Are there ground-based efforts contributing on a similar massive scale?
Oh, absolutely. There are large time domain photometric surveys that monitor how things change over time across large patches of sky. You've got projects like OGLE, MACHO, PAN-STARRS, the Sloan Digital Sky Survey, SDSS, the Zwicky Transient Facility, ZTF. They find supernovae, variable stars, all sorts of transient events. And looking ahead, the Vera C. Rubin Observatory, formerly LSST, will provide multi-epoch photometry and astrometry reaching much fainter stars than Gaia, especially in the southern hemisphere.
So more light curves, more positions.
What about the chemistry, the composition? That's where the large spectroscopic surveys come in. Things like RAVE, Segway, Apogee, Lamost, and Gala. These measure radial velocities for millions of stars, but crucially, they determine the detailed elemental abundances on stellar surfaces, what the stars are actually made of. The Gaia ESO survey, for example, specifically focused on providing abundances of heavier elements, including those created by the slow and rapid neutron capture processes, the SES process, and R process. These tell us about nucleosynthesis in previous generations of stars.
Okay, so we have this absolute explosion of increasingly precise data pouring in from Gaia, from Kepler tests, from all these ground-based surveys. Given all this incredible new information, where are the stellar models still struggling? What are the big challenges that this data is actually highlighting?
Yeah, that's what's so fascinating here. The sheer accuracy and volume of the new observations aren't just, confirming the models we already had. They are actively pushing us to improve them by highlighting areas in stellar physics that are still poorly understood or not fully accounted for in current models.
So the data is revealing the gaps in our knowledge.
Exactly. It's revealing the frontiers. This is where the new data is showing us where we need to do better.
What are some of those specific, tricky physical mechanisms? Where are the models falling short?
The source lists several key areas needing improvement. Often these are highlighted by tiny discrepancies between model predictions and really precise astroseismic data. These include properly understanding how rotation affects mixing inside a star, how material gets moved around, the impact of magnetic fields, especially how they influence stellar activity, star spots, and maybe even the internal structure, tidal effects in close binary systems, how the stars distort each other.
What else?
Thermohaline mixing, that's mixing driven by differences in both temperature and composition, which can happen in certain evolutionary stages. The role of gravity waves, internal waves, not gravitational waves from black holes in transporting energy and angular momentum inside stars. Accurately modeling mass loss from the star's surface. How much material stars shed, especially in later stages, significantly impacts their evolution.
And even fundamental inputs are still being refined.
Yes, things like the precise rates of specific nuclear reactions. The source mentions the 12C alpha gamma 16O reaction fusing carbon and helium into oxygen. Getting that rate exactly right is crucial for predicting the later evolution and nucleosynthesis, but it's experimentally very challenging.
Are there also challenges in the numerical techniques themselves, how the models are built?
Yes, there are. For example, the source mentions the development of 3D atmosphere models. While the full stellar evolution is typically computed in 1D, basically, assuming spherical symmetry to make it computationally feasible, these more complex 3D simulations of just the star's outer layers are crucial.
Why? What do they help with?
They help calibrate the simplified empirical parameters like those used for convection or for modeling how the oscillations are excited that are then plugged back into the faster 1D evolution codes. Also, getting accurate predictions for how elements are created in nucleosynthesis, especially the heavier elements made via the S process, requires very detailed modeling of later evolutionary stages, like the asymptotic giant branch, AGB phase. Modeling that phase well is also essential for interpreting infrared observations of evolved stars and stellar populations.
And what about stars that aren't alone or have stuff around them?
Right. Detailed models are being developed for complex systems like common envelope binaries. That's where one star actually engulfs its companion. Understanding their light curves requires sophisticated modeling. And looking ahead, future instruments like the Extremely Large Telescope, EELT in the optical, and the Square Kilometer Array, SKA, in radio will allow really detailed studies of the circumstellar envelopes, the gas and dust around massive stars. That will help us model their structure, how they lose mass, and even probe their magnetic fields.
Okay, so we've got observations pouring in, highlighting these physics challenges that need better modeling. What enables scientists to actually bridge that gap? How do they connect the raw data to these incredibly complex theoretical models?
Well, absolutely essential to this entire enterprise are the major advances we've seen in software infrastructure, computing power, and data storage over the last, say, couple of decades. These technological leaps are completely transforming how stellar theory, numerical modeling, complex simulations, and the observational data all interact and are confronted with each other. It's a whole new way of doing science.
Can you give us a sense of the software landscape? What tools are people using?
The source lists a whole suite of software tools being used across the field. Things like Astropy, which is a core package for astronomical calculations in Python. There are codes like Athena++ and FlashX for hydrodynamic and magnetohydrodynamic simulations. GYRE for calculating stellar oscillation frequencies. PAEB for modeling binary stars. TARDIS for simulating radiative transfer in supernova ejecta or other outflows. It's really an ecosystem of specialized tools, each tackling different parts of this incredibly complex problem.
Is there one particular software initiative that maybe stands out as a major hub or framework.
Yes, the source specifically highlights the modules for experiments in stellar astrophysics, or MESA. It's described as a really significant open knowledge software project.
Yeah.
Open source, community driven, it really gained momentum after its initial release back around 2013.
And has MESIC kept evolving? Is it incorporating all this new physics and computational techniques we've been talking about?
Definitely. The source points to significant updates in the latest version, which came out in 2023. These include new methods for treating time-dependent convection, which is really important for massive stars in their very late burning phases, just before they explode. They've updated how they handle stellar atmospheres, improve the treatment of various kinds of opacities, molecular, Compton scattering, conductive opacities. There are updates to how elements diffuse within the star, updates to nuclear reaction rates, new treatments for how the core crystallizes in white dwarfs. They've even added ways to model star spots on low-mass stars, which connects back to those buoy Draconis variables Gaia sees, and better handle superadiabatic convection in regions dominated by radiation pressure, which happens inside very massive stars. It's constantly being improved.
It really does sound like this continuous accelerating cycle, doesn't it? You
Yeah.
get new, better data that reveals where the models are incomplete, which drives the development of more sophisticated physics and numerical techniques, which get incorporated into powerful software like MESA, which then helps interpret the next wave of even better data.
That is absolutely the core feedback loop driving progress in understanding stars right now. It's incredibly dynamic.
This has been a truly fascinating deep dive into how astronomers are tackling the interior lives of stars. It's just mind-boggling. To wrap things up, the source shares a wonderful anecdote that kind of puts the complexity we've discussed into perspective.
Ah, yes, it's a classic story in astrophysics. John Faulkner recounts attending a talk where the famous Fred Hoyle, known for his big picture thinking, started by saying something like, "Oh, basically a star is a pretty simple thing."
Simple, after everything we've just heard.
Exactly. And apparently, from the back of the room, the observational astronomer R.O. Redman quietly but famously retorted, "Well, Fred, you'd look pretty simple too from 10 parsecs."
Huh. That perfectly captures it. A matter of perspective and distance.
It really does. And the source uses that story to underscore that Gaia, by observing stars from many kiloparsecs away across the galaxy, but with such unprecedented precision and detail, it's showing us just how incredibly complex stars really are, even the seemingly common, boring ones. And this complexity, far from being discouraging, is exactly what's challenging our models and driving this incredible period of progress we've been discussing.
It really makes you appreciate the scale of the scientific endeavor, trying to understand these distant, complex objects, and it leaves you wondering, given the incredible complexity being revealed by new data like Gaia and the leaps in modeling, what fundamental new physics might we still uncover about even the most familiar stars out there in the universe, things we haven't even thought of yet? That's definitely a powerful thought to consider. Thanks for joining us for this deep dive.